Hi, welcome back to this video series on cryptography. Today I'm going to talk about privacy homomorphisms, a topic that I touched upon in my other video on homomorphic encryption. I went back in time a little bit. Well, it turned out to be 1978. There was a paper written on homomorphism, data banks and privacy homomorphism from Ron Rivest, Len Edelman, and Michael Redozos. They're talking about a pretty neat idea of being able to do computation on ciphertext. This idea turned out to be a novel idea that I'm going to speak a little bit about a few of the important topics they discussed here. This is not a complete review of the full paper, but only a selected subset of privacy homomorphisms to start with. So it is very interesting that today cloud computing is a huge topic in many companies. And actually, back in time, even in 1978, they thought about this idea of cloud computing. They didn't use the word cloud computing, as far as I know, in this paper, but they have this notion that I will talk about. For example, the figure that you're seeing, figure 1, shows a situation like this. You have your physical perimeter, secure perimeter. Maybe you have a bunch of computers here within this physically secure perimeter. And you're using a time-sharing system, which you can replace it by a cloud computer if you want. So on your right, you see here is the cloud computer. You store data in the cloud. So basically, the data bank files are cloud, stored in cloud. And whenever you want to do processing, you actually download it from the cloud and then process it right locally on your machine. Of course, you will not trust the cloud, so you would have to do encoding or encryption. They call it here actually encoder, but it's usually encryption, just to avoid any confusion with encryption and encoding. So encoding means, in this case, encryption. You upload the encrypted version to the cloud and then download it, decode it, and do the analysis locally on your machine. So this seems to be an okay idea, but it's a little bit inefficient. You have to encrypt first, you have to download it, you have to decrypt it, and then all these things have to repeat multiple times. So wouldn't it be nice if you can do analysis on the encrypted data? So you have a bunch of data, you have encrypted it, you upload it to the cloud, but on the cloud computer, you want it to be able to run some analysis. For example, they're talking about a simple bank, a loan processing company context. It's a hypothetical example, but still very relevant to the practice. They want to be able to answer some basic questions like, okay, what is the size of the average loan outstanding? How much income from loan payments is expected? How many loans over 5,000 have been granted? That kind of questions. Wanted to be able to answer without decrypting the data. So this idea is pretty novel, even very applicable today. Many cloud computing systems would benefit from such a homomorphism concept. So let me now dive into what I mean by homomorphism. Mathematically, I will explain that, and then I will show you some analysis that we can do with the homomorphic encryptions that they have shared in this paper. So I'm going to pick a few things that I will touch upon, privacy homomorphisms. They have defined mathematically the details, but I am going to sort of abstract a little bit of mathematics as much as I can, and then explain some core ideas. Okay. In this paper, they talked about the idea of using a homomorphism like this. Let me explain this homomorphism. So what you're seeing here is basically an example number 3 in this paper. You have a bunch of, say you have a lot of data, and you wanted to upload that data after encrypting it locally to the cloud. So one function that you could use is this function that you're seeing, pi inverse of x. Okay, x is your data. Okay, x is basically a number in set Zn. Zn stands for all numbers from 0 to n minus 1. Okay, Zn. You upload that by first take your x, the data, the secret that you would like to encrypt. You take your x and apply mod p first. Mod p means you find the remainder after dividing it by p. Let me explain what p and q in a moment. So, and then you do the same with the x mod q. So you have a pair of numbers. So your input x is transformed into a pair of numbers, p and q. So P and Q are actually two prime numbers that are multiplied together to form the number n. Okay, so the security assumption here is that given n, it is difficult to find P and Q. Okay, as a matter of fact, in this case, the cloud computer doesn't even necessarily know n, right? You're only uploading x mod P, x mod Q. The cloud computer doesn't know Q nor P. So it will be difficult for the cloud computer to find the x given the pair x mod P and x mod Q. That is the assumption here. Okay, so this seems to be like a pretty neat formalism. One example actually of homomorphic encryption. The theory behind is very nice. This function pi inverse of x is actually a one-to-one function. Given an x, okay, there is only one x mod P, one x mod Q. Okay. Similarly, given x mod P, x mod Q, there is corresponding only one x. Otherwise, this is useless. Okay. So this is a very nice concept. So I'm not going to prove this function pi inverse of x is a one-to-one function. So I leave that as a simple exercise. As a matter of fact, pretty much any number theory book that talks about homomorphism would have a proof on this. Okay, number theory or algebra book. Okay, so I leave that. Now let's focus on some concrete examples and do an analysis of this particular homomorphism that we are interested in. So for that purpose, I will first explain a little bit of formalism, and then we will dive into the details. Okay, so I'm going to sketch this a little bit, right? So what we are going to do is actually, X is our secret, right? Which we wanted to upload to a cloud. So what are we trying to do? We don't upload X, otherwise everybody will know the secret. So what we do is we basically map this X into X mod P and X mod Q. Okay, so this is computed locally before you upload to the cloud, of course. Okay, so what is the benefit of doing this X mod P, X mod Q? Okay, well, this is something I would like to explain to you with examples. For example, say your number is n is 15. Okay, let's say n is 15. Just a toy example to get the idea across. And that means P is equal to 5 is one prime number. There's only unique way of writing a number as a product of primes. So P is equal to 5, Q is equal to 3. Okay. Of course, you can swap P and Q, but it doesn't matter. Order doesn't matter. So anyway, so given n, P and Q, now suppose your number is say 6. Okay. Suppose your X is 6. Okay. How will the 6 be stored in the cloud computer? You don't store 6 as it is, of course. You do 6 mod P, which is 6 mod 5, which is 1, and 6 mod Q, which is 0. Okay, so you store 1, 0 in the cloud. Okay, so let's consider another number. Say, let me call this as x1. Okay, and x2 is equal to say 4. Okay, it's also another secret. You don't store 4 as it is, otherwise everybody will know. So you will do mod P and the mod Q first. So which means 4 mod 5 is 4, and 4 mod 3 is 1. Okay. So now you will be uploading this to the cloud computer. The cloud computer knows 1, 0, 4, 1, nothing about your X, not about P or Q or N. Okay. So what can we do with this? As a matter of fact, you can make the N to be public. So that's not a problem. Okay. N can be public. N can be public. P and Q are private, of course. Okay. Otherwise, this whole system is broken immediately. Both P and the Q are private, just to be clear. All right, so what can the cloud computer do? As a matter of fact, it is a good idea to keep n to be public, because the cloud computer can also do mod n, otherwise the numbers will become much larger. Okay, so this is basically the assumption here, right? Now I'm going to show you some interesting benefits of doing this transformation. Say you wanted to add 2 numbers. Okay, in your original set, what is 6 plus 4? 6 plus 4 is 10. But we can let the cloud computer add the numbers for us and get the answer, and then we will do a transformation. Okay, we do know 6 plus 4 is 10, of course. But what about 6 in the cloud computer? 6 is 1, 0, and 4 is 4, 1. Okay, so now these 2 numbers will be added by the cloud computer, and it will become 5, 1. Remember, the cloud computer doesn't know P into Q, so it cannot reduce this number any further. Okay. So what you have is actually 5, 1 in the cloud computer. Now the cloud computer is sending you 5, 1. So now you can do your magic. With 5, 1, you wanted to go back to the original number x1 plus x2 is your goal, right? So you have to do a inverse transformation now. So given 5, 1, how can you find the original number? Okay. So now let me show you a program that I wrote. Then we will use this example there. Okay. So I'm going to now apply the Chinese, Chinese remainder theorem is basically the underlying idea, but we can do a simple transformation very quickly with the help of a program. So I'm going to show you my program now. So what you're seeing is my program written in Python to the left, and I'm now just going to straight away run this thing first. Okay, so I'm in the Python mode already. All I have to do is define these variables, right? P is equal to 5, Q is equal to 3, N equal to P times Q. So I have, I wanted to be able to add x1 is 6, right? And what was my other number? X2 is equal to 4. Okay, so these are the numbers that I want to add. X1 and X2, when I add it is 10, but let's do it without knowing P and Q. Okay, so first we need to project our numbers into the set ZP and ZQ pair, right? So what will happen now? My 6 will be transformed into 1, 0, and 4 is transferred into 4, 1. That I have shown you on my whiteboard. So what I'm going to do is very simple. I'm going to take my pair, which is after I add these two numbers, what did I get? I get 5, 1, right? That's what I talked about on my whiteboard. Now I'll get back to the, let me show you that one very quickly. So what I have on my whiteboard is 5, 1. So how can I get back from 5, 1 to the original point in Zn? Okay, that's my goal now. So let me go back now. We have 5, 1. So we can actually leave out the x1, x2. It's not important now. X is 5. We usually use the word xp to denote the first coordinate is 5, and the second coordinate is yq. That's one notation, or xq is better. Xq 5, 1. Okay, so now we will apply the Chinese remainder theorem idea that will invert this xp, xq, p, q, and n. Hopefully get 10. Yeah, we got 10 back. So what you saw so far is a simple demo of adding two numbers in the cloud. Okay, so when the cloud adds these two numbers, what happened? Let me go back to my share again. So in the cloud, we did this addition, right? So the cloud computer sent back 5, 1 to the user's computer. The user now knows the private keys P and Q. So he applies Chinese remainder theorem on 5, 1 to get back the answer 10, which is exactly the answer the user would have got if he does x1 plus x2 is equal to on his local machine. So this is one homomorphic transformation. So meaning you don't do computations on the large set, right? Your large set is Zn, which is made of numbers from 0 to 14 in this case. You actually map this into smaller sets, ZP, ZQ pair. Okay, this is basically what we did. And now we uploaded this set to the cloud computer. And the cloud computer has, of course, operations like plus, minus, and so on, multiplication. It was able to do this on in the cloud and sent us the result 5, 1. With 5, 1, we know the private key, we recovered the original answer. So we have not done decryption of each and every data. We just did computations on the ciphertext in the cloud. So that's the beauty. Okay, so this hopefully clarifies the idea. So let me now show you one more important idea rather, is how do we do multiplication? Multiplication also can be done very easily. We can just map this to mod p mod q as I shown you earlier, and then we do multiplications and then we do inverse. That's perfectly fine. Okay. what is more interesting to notice is this problem. When I discussed about Z15, which is made of numbers from 0 to 14, we took two numbers, right? We took the number x1 to be 6 and x2 to be 4. Okay, we uploaded the mapping of 6, 4 to the cloud. 6 became 1, 0 because our P was 5 and Q was 3, right? Let me write it here. P is equal to 5, Q is equal to 3. Okay, and now x2 equal to 4 became 4, 1. So we uploaded these two numbers. There's one fundamental problem that is with this encoding scheme. We cannot compare whether one number is less than or equal to or greater than. That kind of comparison is not possible. See, the reason being very simple. We do know that 6 is greater than 4, right? In Z15, that's true. However, we have a problem. 6 became 1, 0. 4 became 4, 1. Okay, although 1, 0, if you define the less than like this, right? Less than means compare the individual components. This is true, right? 1 is less than 4, 0 is less than 1. Therefore, this is true. But on the original set Z15, actually 6 is greater than 4. So we cannot do a less than, greater than, equal to, that kind of operation, unfortunately. And that's the reason why, one of the reasons why this simple encoding scheme that you're seeing wouldn't work, because a loan company may want to find out, find all numbers or find all loans that have balance of more than 1,000. That cannot be queried easily by the loan computer using this encoding scheme. Okay, so that's one problem. Another problem is actually more fundamental problem. So let me now write a little bit of math here now. So our x, which is in Zn, gets mapped into x mod p and x mod q. Okay. All right. The problem is that what if our x is so small, right? Maybe in the context of a loan processing system, maybe people have loans, but they are not that large numbers, right? You know, even if it is several trillion, it's just still small number from a cryptography perspective. Because remember this problem of factoring, given n to find p and q is actually known to be difficult for very large n, you know, meaning when n is made of 2048-bit number and so on, like 700-digit number and so on, but nobody has 700-digit loan as far as I know. So this is the problem that when your x is smaller than p, usually in cryptography, let's say n is 2048-bit number, p and q are about 1024-bit number. Still, 1024-bit number is a very large number, and hardly anyone has a loan for 1024-bit. Okay, so that means this x mod p and x mod q actually reveals the original x. You know, that's the problem. X mod p is same as x when x is less than p, and the same with the x mod q as well. So the secret x is revealed when you apply this transformation. Okay, given a secret x, apply x mod p, x mod q, wouldn't work if your x is so small. So you have to sort of make sure that your x is bigger than p and q. Otherwise, the scheme wouldn't work. Nevertheless, it's interesting to look at it from a mathematical perspective. Given x, you transform into 2 different points, right? So your point is coming from Zn. Instead of doing computations in Zn, you will be doing computations in Zp, Zq, and that's pretty neat. And that's the basic idea of homomorphic transformations, right? That one point is essentially equal to other point in another set of space. Okay, so that's basically what I want to talk to you. And in the later videos, I will show you some more details about other homomorphisms that I am looking into. Thank you very much.